What is up, current tech fans? Welcome back to another garage tinkering video. And in this very special episode, we've got a returning guest all the way from North Carolina, I believe. Matt Kaiser from Kaiser Engineering is joining us. How are you doing, Matt?
I'm good. How are you doing?
Yeah, pretty decent. It is a lot later here for me than it is for you, but other than that, doing pretty well. So Matt is joining us today because we are looking at how to protect your PCBs from automotive environments, which are notoriously problematic. They come with a load of issues. And very recently, I've obviously released my first gauge board, and Matt has been a huge assistance on designing a lot of the components and the electrical engineering side of that, and has also designed the power protection board that a lot of you have picked up as part of our little bundle, and has been responsible for making sure that none of these gauges blow up in any of your cars. So we're going to look at some of the problems that are brought up by a car and dirty automotive signals, and the steps you can take if you want to protect your PCBs from those things. So we're going to start by taking a look at the schematic diagram of the board that Matt has kindly created. And as we can see on this left-hand section, we've got a few protections and the things that these components protect against, which are overcurrent, reverse polarity, and transient protection. So Matt, if we were to start with the first of those considerations, overcurrent, what exactly is that and which of these components protects against it?
Overcurrent, in an automotive sense, is going to be essentially any case scenario where either the downstream device, that could be your power supply or your display module, if that were to have a fault and start shorting power, you need a way to protect against that. Or another case scenario, if your PCB were to make contact with, say, the chassis of your car, that could essentially create a short. And what you want to do is you want to create some way to protect your circuit from not drawing too much current. And there's two cases. Ideally, it just blows a fuse. Or the other case, it could heat up and cause damage to your car, a fire. So you always want to have some kind of protection. So to do that, we've added a fuse. And this is set up as it's called a PTC fuse. And that is going to be, essentially, it's rated just enough where it's going to allow normal operation. But if anything were to start shorting or go over current, that's where this fuse is going to kick in and protect the circuit.
Presumably the size of the fuse that you pick is highly dependent on the environment and the amount of voltage that you want to put through. So what brought you to the decision of actually picking this specific fuse? What's it rated for?
Yeah, so this fuse is rated for, well, we'll start with voltage. In an automotive environment, you're working with around 15, 16 volts once the alternator is running. When I design circuits like this, I like to overprotect because automotive environment has a lot of voltage spikes. It's not clean power. For example, this fuse is rated up to 33 volts. That is definitely overkill, and we'll go through later of the other protections where I am confident I know I will not exceed this 33 volt rating. You want to have it where it's not going to impede the operation of the actual downstream device, but you also want it to kick in when it's absolutely necessary. And that's very important with a PTC fuse because that operates different than a standard fuse. A standard fuse where it's going to blow at a certain current, that's going to act fast. That's going to be split second over current, you'll blow a fuse. Something like this takes a little bit of time to heat up and then disconnect the circuit. So it still is within a second or two, but that's still enough time. We do want to stop that. So you want to get that to the limit of what your device is going to operate at, but not too close. Two key parameters when we chose what fuse to use here. It's going to be the hold current and the trip current. Hold current is going to be we set that to 1.1 amp. And what that means is anything below that, it's going to operate exactly the same. There's going to be no resistance. It's going to act as just a pass through. Anything above that, up until the trip current, which the trip current will be 1.95 amps. Anything between that, it's going to start blocking the current more and more. It's going to act more resistive. It's going to start heating up, and that's on purpose. So that's that range where these fuses are a little bit more, they have higher range where they trip, because we're talking almost, what was that, 0.8 amps difference. So we want to make sure that we're right there at that limit, that 1.1, and a little bit over. If your device has some current spikes, it's not going to trip it. And when I say trip, it's a slow acting thing. So you can go above it, it's fine. So that's where that 1.1, we want to stay below that for normal operating conditions. And for anyone that's trying to figure out exactly how much power this can support, you do have to think in the frame reference of wattage, not current, because when you're picking one, you do look at amperage, but when you're thinking about how much can my system support, you got to think in wattage, because we're stepping down to 5 volts. So if you think about 12 volts running at 1 amp, we'll say 1 amp just for easy math, that's 12 watts. If you want to find out how much current you can provide at 5 volts, you would do 12 watts divided by 5 volts, and that'd give you the amperage. So the amperage will be higher. So don't see this as a hard limit.
So moving on, reverse polarity. Tell us what reverse polarity is, and which of these diodes, right? Well, which one of these two is helping us with that?
Yeah, so for reverse polarity, why that's needed, in a vehicle, you can have voltage spikes, and those can sometimes go both directions, especially with the motors. They can create a back surge of power, of voltage coming in. So we put D1, that component is there to protect from reverse voltage, which reverse voltage means there's power on your ground plane, and that can destroy components or destroy boards. So we chose to put D1 right after the fuse. It's the next line of defense when it comes to making sure your circuit board is protected. The key thing here is that you want to make sure that a surge is not going to surpass what's called the reverse voltage. The reverse voltage of a diode is essentially, all diodes are one-way circuits to a limit. At a certain point, they are going to, if you exceed a certain voltage, power will flow backwards. And at that point, it will destroy downstream devices. So for this, we chose something extremely high because, again, like I said, automotive environments can be very brutal on circuit boards. We chose to use a reverse voltage of 40 volts. What that means is this will protect up to 40 volts in the reverse direction. So essentially putting power on ground and ground on power.
Obviously something that you try to avoid. Don't wire your battery up backwards, and don't jumpstart yourself wrong.
Yep. And then just everyday use, you can sometimes see a surge of power. So
yeah,
this is just good practice and should be in any automotive device as some kind of protection against reverse voltage.
This was a really scary one to test on the board, because the only way to do it is to put power into the ground and ground into the power, then press the little on button and hope that nothing weird happens. But fortunately, I stuck 14 and a bit volts into it in reverse, and just nothing happened. So that's like the golden ticket. It's exactly what you want.
And this, in that test case scenario, you could apply 30 volts, 40 volts, and you'll be perfectly fine.
Let's keep moving forwards with transient protection. For those who don't know, what are transients?
Yeah, so transients will be essentially very quick pulses of energy, and that can be from, I guess, in automotive case, that can be something like your starter kicking on, and the solenoid, that instant voltage spike, any kind of ESD, and that could be like a shock from you handling the device. That could even cause this voltage to be applied immediately, instantaneously, and that could fry the downstream. But essentially, in the normal use case, this is just here to prevent anything that's going to come in on the input that's above 42 volts, which we can talk about that later. 42 volts is kind of our hard limit. And this is going to essentially try to squash any of those pulses coming in. Think of a big wave of energy coming in. You're trying to dissipate it, but you don't want to dissipate the normal stuff coming in. So that's what this is set up for.
So it just kind of like takes the top edge off.
Yes, so it's there to essentially kick in if power spikes too much. And this all happens extremely quick. This is not going to withstand an overvoltage where if you were to give it 60 volts, you will destroy it. Hopefully the fuse kicks in by then. But this is meant for a quick, instantaneous 50, 60 volt pulse, something like that. It's supposed to sink that current away and protect everything downstream. And that component is going to be D2, and that's a TVS diode. So that's, again, there to protect from overvoltage and surges of power. So when you're choosing a TVS diode, you want to look at your normal operating conditions and give yourself a little bit of headroom. So like we were saying, a automotive environment runs at about 15, 16 volts. So I chose to use a diode that has what's called standoff voltage of 18 volts. What that means is after power or after voltage starts exceeding that 18 volts, it's going to start sinking that current. So it's going to redirect the current from the downstream device into our ground plane. Essentially, that's going to start shorting it, pulling that extra surge of energy away. Typically, those pulses and those waves of energy are not high current. They're instantaneous pulse, so it's okay to just sink it away really quick. And this TVS diode is, like I said, 18 volts is when it starts kicking on, but it doesn't actually start clamping, which is the upper limit. It's called the clamp voltage, and that voltage is 29.2 volts. And what that means is at 29 volts, it is going to short everything to ground. That is, at that point, that's a high voltage, high surge. It's going to sink everything possible, and it's going to protect your downstream device. When we chose that because when we're looking at our switch mode power supply, that can handle up to 42 volts. So if we have a clamp voltage under what its max limit is, we can essentially ensure that it'll never see a surge of power that is greater than its limit, because we got this TVS diode that's going to sink all the surge of energy to the ground plane and protect the rest of the circuit.
And I guess really on this circuit board, what we're talking about, that switching power supply, that is the heart, the beating heart of this kind of thing. And that's the expensive components that we really don't want to blow up of all the ones on this board.
Yes, this is the expensive component and the complex component.
I don't want to get into like too much granular detail about the component choice, but you were quite adamant with that particular choice of component, and apparently you were telling me it was one that you've used in these kind of similar things in your own boards. What exactly is that component choice, and why is it that it's such a good choice for this kind of system?
Yeah, so when it comes to picking a switch mode power supply, I'm really happy with this power supply because essentially it is extremely high efficiency, which is, in my opinion, very important when it comes to automotive use, because there's two things that are good about efficiency. It's going to be, if it's always on in your vehicle, you want that to drain the least amount of power as possible. If, say, your engine's not running, it can last essentially longer. And the other thing that you gotta remember is inefficiency is heat. So the more efficient, the less heat. And in the automotive world, heat is your worst enemy.
So before we get to this power supply, we've got this array of bulk capacitance. What's that? Why is it not just 140 micro? Why is it 410 micro?
The reason we've done 4 capacitors is because you want to smooth the voltage coming in, and in automotive environment, you do find that the voltage is not very consistent. So choosing four capacitors instead of one is going to allow for essentially quicker response. So think about essentially the four components will provide power instantaneously versus is just one big one. So it's just going to be faster delivery of power.
Great. Okay, that makes sense. So when you get the larger capacitors, their response time becomes slower because of their larger size.
Not necessarily. It's just like it's more on the lines of a larger one will have the same amount of current delivery as a smaller one, and we'll put an asterisk
Right.
there. Uh, in a general rule of thumb is going to be that they all provide similar current output when you get larger capacitors like this. So you're literally just adding four of them is four times the current delivery, instantaneous. But again, if you go smaller, that instant is much smaller. And we are talking milliseconds, microseconds of response. So that's where it comes in is just four times as fast to respond, but it can't respond for long. So it just helps smooth everything out.
So this thing provides us a very, very stable 5 volts. I've been blasting it with a wide range from kind of like, 9 in up to temporary 30, and it gives us a very stable 5.03 volts out. Yeah, so there's no reason to think that it should really ever deviate from that. With all these kind of components, what would you expect the kind of life cycle of a board like this to be? Has it got potentially an end of life?
No, everything is designed in this board to essentially be one, it's got all the protection needed, so it's never going to see anything out of its limits. So these products should last probably as long as your car is going to last.
I'm
I
not sure how long that is.
yes, so we'll see. It's my little blanket statement there. But I will say I've been using this exact design or just about exact design in the products I use, and those have been in the field for the where it's used the most has been in the field for 10 years, running 100% of the time in the worst environments. I mean, sitting on a dashboard, baking in the sun, and I've, knock on wood, never heard of a single failure. So at this point, I'm very confident in this design. As long as you go through each step and you think about what can happen in an automotive environment, and you just put the components in to protect from each case scenario.
And was when you were picking all of the components, were there any considerations into things like the fact that you say automotive brings along other complications with things like the fact that it is physically actually like with volume noisy as opposed to electrically noisy, and it vibrates and it gets hot. I've got people buying these boards who are in Texas, which is a literal hellscape when it comes to being inside a car. They're telling me about 90 degrees underneath the dashboard. It's like, are there considerations for the actual component choice when considering those factors as well?
Yes, all of these components are rated for industrial level temp. So that's going to be 125 degrees Celsius, which is way hotter than anything you'd see in a car. All of my testing, I expect at most 180 degrees Fahrenheit is what I try to design for when I'm considering product design. Because to my understanding, that's the most you can see. And I've been testing that here in North Carolina. We've had a heat wave the past few weeks, and it's been reaching just about 100 degrees. And I've purposely been parking my car in direct sun, laying my boards in the sun, and running them. So I like to, again, these boards are using the exact same power supply. So that's what I'm saying. When I say my boards, I'm also talking about these boards.
You're a little stress test sadist there.
Yes, and I've put them in the oven, and I will run it in the oven. So I'm very confident these will last and these will handle the heat. Everything about these are designed to be robust and ideally never fail.
One of my personal things was the aesthetic of it all and having it actually fit the footprint and the format of the round boards and be able to. So I when I was designing the gauge board itself, deliberately tried to put standoff points where we would be able to mount a duplicate or a daughter board, which I guess this is, alongside it. And I guess there was a couple of challenges there with this like weird little shape that we ended up with, where we could still get the USB and all the various JST connections in and around.
Yes, definitely like to make it difficult.
But it looks so cool.
It does look good. Yeah, it's cool.
Okay, and it's the form factor is great. You know, the whole goal with this whole system was to have it so that these things would fit a kind of like a normal off the shelf 16mm gauge pod. And when I finish the enclosure at some point very soon, that'll hopefully be that achieved. And I do think these things look very cool together. So I think we've gone over everything in here. Is there any other factors that you considered other than like rule of cool?
I mean, without going super in depth of the chosen components for just configuring the switch mode power supply, I would say not especially. It's everything else is just kind of reading through the data sheet and just understanding how to properly set it. With maybe the only thing that's a little bit worth considering is the output. You also want to have, like I was saying, same thing for the input, you want to have some bulk capacitors on the output as well. That just helps stabilize it, because how a switch mode power supply works is it's actually essentially turning power on and off. So it's not like a linear dropout regulator and an LDO. It's switching power on and off really quick, so you have to smooth that. So this data sheet will call out, based on your voltage, what amount of capacitance you need to stabilize. So that's the only thing, is when it comes to a design like this, you want bulk capacitors to stabilize it as well.
Yeah, and like I say, during the testing, there's been almost no fluctuation. Anything definitely has seemed stable, but it's been on the inside of the house test so far with a car battery that sits underneath my desk. It will very soon be going outside, because the actual next steps of this are impending. It's going to be interesting to see this all actually finally come together. So as we were saying, Matt, you've obviously been using this in your own projects a lot. You've got this really cool display that you have for the Focus. You've just been putting some like cool weird UIs, right? They were a bit, I think, that anything inspired by the Need for Speed Kitty type thing, and you've gone another way, right?
Yeah, so I've been working on my next generation product. It's a digital dash for the Ford Focus, ST or RS. And yeah, I've been now integrating LVGL into it and just testing out some of the fun features it can do, like playing animated wallpapers.
That was very cool. We're gonna have to have a look
Yes.
at that in more detail at another time. But yeah, that seems really, really good.
Yeah, so stuff like that, animated wallpapers, just generating just all different kind of themes. We came out with a grumpy cat theme and stuff like that. And it's just fun. Like the whole idea of your Need for Speed as well, just personalizing and making the whole experience just more personal. And that's what I'm trying to do for the Ford Focus, ST and RS.
Definitely a lot of overlap there. I always like finding people who are in the same like cool but weird mindsets.
Yes.
My people. And if you want to speak to more of these kind of people, myself and Matt included, you can always come over and talk in our Discord. There's a link down in the description. Yeah, lots of interesting stuff. But Matt, that has been a really helpful little look into that. I really appreciate you breaking down what each one of those things does.
Yeah, I'd love to help. I think this is great.
So yeah, thanks so much for your time, and I'm sure we're going to have you back in another video, because you're going to be helping with some of the other components that we're doing as daughter and accessory boards for these for this ongoing project, and I'm sure you're going to do things again that I don't understand, and I need your help.
So I'm here for.
Awesome. I appreciate it, buddy. You have a great rest of the night.
You as well.
So again, massive thanks to Matt for coming on and talking us through that board. Really useful, not only for you, I'm sure, but also for me to totally understand everything that we've been putting together and why all the choices have been made. And hopefully it means if you're going to design PCBs that need to live in an automotive environment and you want to protect them, you have a better idea of A, what you're protecting against, and B, how to go about doing it. If you want to see more of Matt's work, you can head over to Kaiser Engineering on Instagram. I'll stick a link down below. And if you do have a Ford Focus RS and you want one of his really cool little screens, definitely go check out his site. I'll link that down below as well. As always, if you've got any questions for either me or Matt, who I know does read these comments, be sure to stick them down below and we'll get back to you as soon as we can. Otherwise, I hope something good happens to you today, and I'll see you in the next video Wednesday at 2 p.m. Take it easy, peeps. Bye-bye.